In this video, we're going to explore the oxymercuration demercuration of an alkene. The chemicals required are an alkene, water, and mercury 2 acetate. Yes, this is the short form for acetate. This is a little more explicit form of acetate. They're both really the same ion. The end result is a Markovnikov alcohol. The more electronegative oxygen on the tertiary carbon, oxygen electronegativity 3.5, and the less electronegative mercury ends up on the secondary carbon. Mercury has an electronegativity of 2.0, which you are not responsible for. Acetic acid is the side product. It picks up a proton. It is the best base in the last step of this reaction. We'll discuss that shortly. The mechanism starts, as many mechanisms do, when you throw an ionic compound in water. Yes, water is also the solvent here. The fate of many ionic compounds in water is for them to ionize. This bond is fairly weak, metal and nonmetal, highly electronegative nonmetal. Oxygen pulls the electrons strongly towards itself, and this thing ionizes to these two species here. Here we get a mercury cation. It's still mercury 2+. One of the pluses is balanced by the acetate, and the other is a naked cation on the mercury. And the other species is the acetate ion here. The positive mercury is very attractive to the electrons in the pi bond, for reasons we shall discuss shortly. One arrow. Mercury does not have a lone pair to come back and make a triangle. There's no need for this group to leave because this will satisfy Mercury's plus charge and get it back to being neutral. So after this step, we're going to see this result here. This triangle is a triangle, but it's very different than this triangle here. This triangle has two full covalent bonds. This covalent bond right here resulted from this arrow. This covalent bond right here resulted from this arrow, and this arrow caused water to leave. All three of these partial bonds in this triangle, yes, that's a partially bonded triangle, which we will discuss a little bit later. All three of those bonds came from this one arrow. They are partial bonds. Let's discuss this triangle. Firstly, the cation in the middle of the triangle is shared by all three atoms, 2 carbons and 1 mercury. If I had to be very accurate, I'd say it spent a little more time down here closer to the tertiary carbon than the secondary. But I will not be grading such things. I will only look to see that you put it in the middle, somewhere in that triangle. The reason why the tertiary carbon would spend more time with a positive charge, we've been talking about quite a bit, is that a tertiary carbon has more hyperconjugation than a secondary carbon. The 3 partial bonds were caused by one mechanism arrow. That's this arrow right up here. One arrow has 2 electrons in it, so 2/3 of an electron, 2/3 of an electron, 2/3 of an electron. 2/3 times 3 gives 2 electrons. How can this be? Why does this happen with mercury and no other element? Main reason? Mercury, with a mass of close to 200 grams per mole, or 200 AMUs per atom, is a very large atom. This picture is slightly misleading. The mercury is so large that it takes up a space like this, where it's simultaneously almost touching both carbons. You can't do that with a hydrogen. So we don't need real bonds, we just need the mercury close to both carbons. We will treat it like a triangle. Next part of the mechanism is very similar to what we've been doing with triangles all along, including back here. Next step, water does a backside attack on this carbon. Which carbon? The more substituted carbon. And the halogen bond breaks. Here we're going to have water attack the more substituted carbon here with a partial bond breaking. We don't have an arrow that can show that, so it'll just disappear. So let's show the mechanism for that. Water does a backside attack on the more substituted carbon, and the partial bond breaks. Whenever we do a backside attack on a triangular intermediate, we get an anti-result, which looks like this. Here's our intermediate oxonium, which is the conjugate acid of our desired final product. We need to pick an appropriate base that will take this hydrogen. In our previous example, if you watch the video, we went to great lengths to discuss why water was the best candidate to remove the H from here. In this example, we have a better base around. Even though water is the solvent and there's a lot more of it, acetate is by far a better base. We'll do the pKb analysis after we finish the mechanism. So our next step is for this acetate ion right here to grab the H from this oxonium. That will generate both the acetic acid and the hydrogen or alcohol right here. So the lone pair on our acetate, which I drew there, attacks this H, and the sigma bond breaks and becomes a lone pair on the O, and that will cause the final two products shown above. We only have a couple more things to discuss. Why is acetate the best base? And also, what is this short form AC? It's useful. Saves us from drawing this or this. So, it's the acetyl short form. Might as well start with that question. AC is one of the most common short forms in organic and biochemistry. This portion is the AC. I'll make it blue up here so it's clear that it doesn't include the other O. I did not make it blue. It includes just the CH3 methyl attached to a carbonyl. That's what acetyl almost always means. So, nice short form we can use. We could have, instead of showing this, we could have started our mechanism with OAC twice. Like this. And starting our mechanism from the beginning, we would have done something like this. The final thing we have to answer is why is acetate the best base and not water this time? And that's a simple answer. The answer goes as follows. As discussed previously, water's pKb is 17. Acetate is the conjugate base of acetic acid with a pKa of +5. pKb of not chloride. Clearly that was a copy-paste job. Acetate is 14 minus 5 is 9. 9 is a difference of 8 from 17. This is a log scale. Acetate is 10 to the 8th times more basic than water. 10 to the power of 8th times. No, that's 100 million. That's all I'm trying to say. 100 million times more basic for acetate than for water. Much better choice. I hope this video on oxymercuration demercuration has been to your satisfaction, and look forward to our next video.